We're back for another year of Gauge Theory Virtual. I'm very excited that we have Jaewon Lee. And I will be quiet and let him take it away. So, yes, you may start.
Okay. Thank you for having me here, and uh, thank you for attending this seminar. As I know, this is very early morning there, but thank you for attending here. So, uh, the title is on homology spheres of the trivial local equivalence classes, and this is the recent joint work with O. Shaw. So, let me start. So first, the uh, problem is uh, asking if there is a non-trivial linear relation between cipher fiber spheres in the homology cobordism group. So, for instance, this is a generalized version of the existence of the two torsion. So, and more precisely, we can ask like this. So we have a family of homologous spheres, ciphered fibered homologous spheres, and all of them are distinct and does not bound any homologous ball. But is there a non-trivial connected sum which does bound the homologous ball? So this is the question. So So when we considered the two torsion problem, we considered this local homomorphism and the 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 lifting element of the non-trivial value uh, were candidates for the two torsion before Manolas could disprove that. So we also got the motivation from the local equivalence group, which is defined by the local equivalence of Higgs-Floor chain complex with iota. So because for the subgroup generated by cipher fiber spheres, the image of this homomorphism H is known to be isomorphic to the infinite rank subgroup by Dye and Stoffregen. So, and they also gave the explicit basis. So, first one is this Poincare homologous sphere. So I let this as a basis. I let this be zero and sigma 2n plus 1 4n plus 1 4n plus 3 with positive n. So this is B of n. So because we got the explicit basis of this infinite rank subgroup, uh, infinite rank group, uh, we we can find a linear relation for any cipher fiber sphere in this local equivalence group. So every cipher fiber sphere Y has uh, the image which can be expressed in the linear combination of the image of BI. So sorry for this notation. So BI. And uh, recent recent progress with Shaw was uh, to show that the existence of the infinite rank subgroup in this kernel. So because we got linear relation for any cipher fiber sphere Y, if we take the connected sum with the minus of the linear combination, we have a element in this kernel. And but we proved that there are infinite rank subgroup in this kernel, and the linear independence still holds in the even in the rational homology cobordism group. Okay, so this theorem is actually a light application of several theories. So this talk will be more focused on survey on several theories, not owned by us, but at the end, I'll give this application and compare those theories. So let me start with involutive figure for homology. In I'll give a brief sketch. So uh, when we have a closed three manifold Y, uh, Osbach-Szabo defined a chain complex which is called Higgs-Floor chain complex. In this talk, we always consider the minus flavor. So we have CF minus of Y, and Hendricks and Manolescu found an involution, homotopy involution iota on this CF minus Y. And then by taking the mapping cone of 1 plus iota and taking homology, we have a homology called involutive Higgs flow homology. And from this homology, when our Y is a homologous sphere, we have a homology cobordism invariant. So these values are homology cobordism invariant, so they are a map from theta Z to Z because they are integer values invariants. But note that these are not homomorphisms. So in general, it is not easy to compute these invariants for any given homologous spheres because the computation of this homology of the mapping cone is sometimes very complicated. So instead of computing this homology directly, uh, we can also consider the other way to obtain these invariants. So it is uh, called local equivalence. So Hendricks, Manolescu, and Zemke proved that if two homologous spheres are homologous cobordant, then these iota complex are locally equivalent. In other words, there are maps from both sides with iota equivalently induces isomorphism of the homology after the localization. So actually these maps are induced by these homology cobordism on both sides. Uh, so this local equivalence forms an abelian group, which is called the local equivalence class group I, and it is defined by just taking the CF minus Y and iota this pair and the local equivalence of this pair. So then we have a homomorphism to from the homology cobordism group to I, and the tensor product. Sorry, so the connected sum is correspond to tensor, and the orientation reversing corresponds to taking dual. Then the aforementioned homology covariism invariance, the lower bar and the upper bar, and the other bunch of homomorphisms, infinitely many homomorphisms, phi n, from which are also defined from the involutive Higgs-Full homology, actually local equivalence class. So the all of these homomorphism and non-homomorphisms uh, factors through this local equivalence group. Okay, so sorry for making confused, but the lower bar and the upper bar are not homomorphisms, and phi n is a homomorphism. So these values factor through the local equivalence group I. But but it is still not easy to obtain the local equivalence. So for cipher fiber spheres, there's a combinatorial way to obtain the local equivalence group. So I'll introduce it briefly. So it is called symmetric gradient root. For every cipher fiber sphere, it bounds a negative definite plumbing manifold, and by taking the minimal plumbing graph, Nemethy defined the uh, a tree combinatorially from the plumbing graph. So the tree is called graded root, and it looks like this. So it is upward opening tree with the infinite stem. And for each vertex, it has a even integer valued grade. And Nemethy also defined combinatorially from this graded root an algebraic object which is called lattice homology. And he also proved that this homology, this lattice homology is isomorphic to the Higgs-Floor homology. So after Hendricks and Manolescu found an involution on Higgs-Floor chain complex, uh, Diane Manolescu also found an involution on these lattice homologies. So here we have some canonical involution here, and they proved that these isomorphisms are also equivariant with respect to iota and J star. So more precisely, they constructed a chain complex from the graded root with the symmetry. So it is called symmetric graded root, and they constructed uh, a chain complex with an involution. So they proved that this is locally equivalent to this complex. Moreover, mm, they they also gave more simple subroot of R, which can determine the local equivalence class of the whole graded root, and hence the local equivalence class of the Higgs floor chain complex. So this sum root is called monotone graded root. And this is just a subroot satisfying some rules. And it is parameterized by two finite sequences, Hi and Ri, as satisfying H1 is the upper bar and Rn is the lower bar. So this is the example when Y is the Briscoe sphere 3, 4, 13. So in this case, the the monotone subroot can be parameterized by m of 0 and minus 2. And we will see more examples of monotone graded subroots. So here is the aforementioned 1, 3, 4, 13, and this is the result by Dai and Stoffregen about Bn. So they computed the monotone graded subroots of Bn, and it is parameterized by 2 and 0. What about 2, 3, 5? So in this case, we know that the lower bar and the upper bar are all of them are 2. So our monotone graded subroot is parameterized by 2, 2, and it is just a single tower. So from now on, I just regard monotone graded subroot as a local equivalence class. For instance, I use the equality for the local equivalence between them, or using plus or minus for m and m prime or something like that. So Diane Stoffregen gave a theorem which I will call decomposition theorem. So the theorem says that any monotone graded subroot is decomposed into this form. So s- it, it is decomposed into just monotone graded subroot of two parameters with these tuples first, H1R1 to HNRN, then minus H2R1, H3R2, and HNRN minus 1, up to local equivalence. So for instance, the monotone subroot M of 4n, 0, and 2n, 2n is decomposed into M of 4n, 0, plus M of 2n, 2n, minus M of 2n, 0. So recall that the previous result for Bn, so this is the monotone graded subroot of B of 2n. This is B of n, and this is again the single tower with the top grading is 2n, right? So we have this as just a tensor of n copies of single tower with the top grading 2. And then we can regard this as n of m 2 of 2, which correspond to B0, right? So we got the corollary actually by corollary by them. So the image of the homomorphism H is generated by M2N0 and M22. So HBM. So from this decomposition theorem and by using the previous computation results for certain Briscoe spheres, we we get some linear relation. So Carcourt and Schauk previously proved that for these families, for Y1n, which is sigma 4n plus 1, 6n plus 2, 12n plus 1, has the monotone graded subroot parameterized by 4n 0 and 2n 2n. Similarly, Y2n, sigma 4n minus 1, 6n minus 2, 12n minus 1 is parameterized by 4n minus 2, 0, and 2n 2n. So by applying the decomposition theorem, we have this linear relation in the local equivalence group. So by taking the connected sum of the left-hand side and minus of the right-hand side, we have the kernel element of H. So from now on, to obtain linear independence of them, we will move on to the survey on the instanton floor theory, filtered instanton floor theory. So let me start with the ordinary one without filtration. For a homologous sphere Y, we consider the space of SU2 connections on the product space, product bundle, product SU bundle over Y. So it is just the Y times SU2. And there's a functional which is called Chern-Simons functional defined on this connection space. And because every value is invariant under the degree zero map action from Y to SU2, this functional factors through this quotient space, which is called configuration space. And we will only consider the irreducible connections, which means the stabilizer subgroup is just the constant map from Y to the plus minus identity. So roughly speaking, we will consider an infinite dimensional analog of Morse complex with functional by taking the Chern-Simons functional, perturbed Chern-Simons functional. So we consider the set of irreducible critical points of perturbed Chern-Simons functional and floor defined the integer valued function of this set. It is called floor index and it is an analog of Morse index. And if we have two critical points and satisfying this index, we can consider this one-dimensional moduli space of anti-self-dual solution on y times r. So it's a connection, and A of t means it's restriction of y times t, and it goes to B or minus or A according to t goes to infinite or minus infinite. Then the instanton floor chain complex of Y is defined as uh, this. So the generators are the irreducible critical points of index I over C. And the boundary map is A goes to B with the index I minus 1, and we can count the the one-dimensional moduli space quotient R because this is one-dimensional. So by quotienting out by R action, we can count the number of the these moduli spaces. So from now on, we also consider the reducible connection. So let theta be the product SU2 connection. So this is just a trivial connection, and so this is reducible. And Donaldson defined the cochain from the first chain complex by defined similarly with boundary map, but counting one-dimensional moduli spaces from A to theta, the reducible one. Then he showed that this is a well-defined cochain, so it forms a cohomology class in the first cohomology, and the theorem is if Y bounds a negative definite for manifold without any condition on pi 1, uh, this obstruction class vanishes. And Nozaki Sato Taniguchi refined this version of instanton floor homology by introducing filtration of Chern-Simons functional. So let me first let this lambda, be the image of the Chern-Simons functional of all irreducible critical points. So is the set of all critical values of the irreducible ones. Then this is locally finite, which means whenever we take a bounded interval, then in the interval there are only finite points. And we also let L of Y as the minimum distance of two distinct points in lambda Y. So for any uh, non-positive S and R, which is not the critical point, we can define the filtered instanton floor chain complex as if S is not a critical value of the functional, then we can just define this we can just define this complex by generated by the subset, the satisfying satisfying this. So the critical value is in the interval of S and R. But if S is a critical value, we just take a bit more interval so that there are no critical points between s minus ly over 2 to s. There are no critical points here, and we define similarly like this. From this definition, they prove many analogies of uh, the ordinary theory. So, for instance, as usual, floor theory, the cobordism induces the the chain map from between two instanton floor chain complex, and we also have a cochain map between uh, cochain complexes, and also for the filtered version. And the Donaldson's obstruction class is also defined for the filtered version, just as the restriction to the the filtered complex. Then it also forms a first cohomology class of instanton floor cohomology. Then when we have a cobordism with the first Betti number 0 and negative definite, then it preserves the floor index, and moreover, it sends the obstruction class to the obstruction class of the multiple of the obstruction class of Y1. So this is always the finite number. So when we want to obtain this, we want to divide by this number. So in the future, we will use the rational coefficient. And from this theorem, we have in particular, if y just bounds negative definite for manifold, b1 is 0, b2 plus is 0, then we just get the exact same analog of the Donaldson's obstruction class, but this holds for any interval. So now we can see that this is a bit more refined version of Donaldson's obstruction class, because when we have this kind of shifting from this interval to this interval, which satisfy this inequality, this shifting induces a canonical map between two chain complex, just defined as the identity if A is also in here, or otherwise it is just 0. Then in this case, Nozaki, Sato, Taniguchi proved that the obstruction class behaviors behaves well under this shifting map. Moreover, uh, when there are no critical points in here, in here and here, then basically there are no changes of the generators, and they prove that this is a chain homotopy equivalence in this case. So from now on, we consider fixed S, and suppose the obstruction class is non-zero, and we decrease R. Then when we get some R prime, we have the obstruction class in this interval vanishes. Moreover, it also vanishes for R2 prime. So we will call this property as birth-death property. So this fact motivates us to define R as invariant to measure when the obstruction class begins to vanish. So now I'll define the R as invariant as the supremum of R such that the obstruction class. But now we consider in Q coefficient is vanished in first instant flow chain uh, cohomology with Q coefficient, as I mentioned. So recall that if Y bounds a negative definite Fourier manifold, then the obstruction class vanishes always for any interval. So now we fix S and we measure when it starts to vanish. So in this case, Rs of Y is infinite for any S. So in particular, if Y is a Seifert fiber sphere, then its Rs is infinite because it bounds negative definite for manifold. And now I'll introduce essential property uh, proved by Nozaki Sato and Taniguchi. So first one is to obtain the linear independence even in rational homology cobordism groups. So if we have a family of homologous spheres and all of our zero values are finite and distinct, and our zero of minus yi is infinite, then all of them are linearly independent in their Q. Moreover, they also gave a convenient formula for certain Seifert fiber spheres. So more precisely, if the integer Stern R invariant is positive, then Rs of minus y is given by just 1 over 4 a1 dot dot an. So now we will give the application of our family. So recall that our family is given by this. So these are our family for the candidate to be linearly dependent in theta 3 uh, with the linear combination of this family, which is basis in the local equivalence group with B0. So we have this local equivalence class, local equivalence. And so to to prove to obtain linear independence of uh, left-hand side connected sum minus right-hand side, it is enough to prove that just all of them are linearly independent. Then it will be easier while it is stronger. So to use these two theorem, we want to check all of them is finite and distinct and minus of the value is infinite. So in our case, the minus is so our yi will be just our cipher fiber spheres. So in this case, all of them have infinite because they bound negative definite form manifold, and it is easy to check that their integers are invariant is one in particular positive, and then we can compute by using this uh, formula. So it is enough to check all the multiples are pairwisely different, but it is different pairwisely just by elementary m- modular computation. And so from now, uh, I'll compare two invariants from both theories. So first of all, I will compare filter instanton floor theory and inverted Hugger floor theory. So because our family has some trivial homology cobordism invariant from inverted Hugger floor theory, but their linear independence could be detected by the RS invariant from the instanton theory. One may ask, is the RS invariant stronger than Higgs-Floor theory? But as a homology cobordism invariant, the answer is no in general. So because I can give some example of family. So consider uh, the Briscoe sphere of this. Then this is one surgery alone. This twist knot, something, but this knot bounds null homologous disk. Disks in positive and negative definite for manifold. So connected sum of CP2 or connected sum of CP2 bar. So this manifold bound both positive and negative definite manifolds. So Rs of y is infinite and Rs of minus y is also infinite. But Hendricks and Manolesk proved that there the lower bar is always minus 2, in particular non-zero. So in this case, RS invariant cannot detect the non-triviality of this homologous sphere, but invariant Higgs flow theory can detect. But as a rational homology cobordism invariant, the only known cipher fiber sphere Y with RS of minus Y is finite is the case when R integer stern R is positive. Then it implies that D is non-zero by Isa and McCoy. So in this case, we don't know which is stronger or not. And now I'll consider pin2 equivariant Seiberg-Witten floor homotopy type and the local equivalence of the Seiberg-Witten theory. So Manoles could define this the homotopy type, floor homotopy type of Y in Seiberg-Witten theory and construct a pin2 equivalent Borel chain complex and obtain pin2 equivalent Seiberg-Witten floor homology. And there are several results on the relationships between several homology theories. So uh, for for Cypher's fiber sphere, the lattice homology and Hughes floor homology are isomorphic, and the Higgs floor homology and the Cyber-Witten monopole homology are also known to be isomorphic. And Littmann and Manonescu also proved that these mhm, this Cyber-Witten floor homology. Uh, so from this, uh, yes, so basically they proved this isomorphism. And And as I mentioned, for cipher fiber sphere, it is known that the standard complex defined from the graded root with the symmetry is local equivalent to the Higgs floor chain complex, involutive Higgs floor chain complex. So Dai and Sasahira and Stoffregen constructed a Pinto equivalent spectrum for the lattice homology. So, and it satisfies that H of R is homotopy, H of R and Cyber-Witten floor homotopy type is pin2 equivariant homotopy equivalent. So from this result, and uh, Stoffregen previously defined a notion of local equivalence in Cyber-Witten floor theory, and with this homomorphism, so we have also local equivalence of Cyber-Witten floor homotopy type. And from this theorem, we have these equivalences. More precisely, if we have two cipher fiber spheres, then the local equivalence classes in both theories, Cyber-Witten floor theory or Higgs floor theory, are equivalent. So, but in this case, the linear relation should be satisfied. So both sides of the relation should be just the cipher fiber spheres, particularly prime manifold, not a connected sum. So we also found another family, and Karkort-Shaw computed the monotone grade sum root of this Y3n, and it it is parameterized by 8n0, which is the same as the monotone graded subroot of B of 4n. So Y3n and B4n are local equivalent in the local equivalence group in involutive Higgs flow theory, but by this by this result, we also have their equivalence in this local equivalence group in Cyber-Witten theory. But with the similar way, we can obtain the linear independence in the rational homology cobordism group. So this is the end of my talk, and there's one more just slide for questions. So first one is already mentioned. So if our cipher fiber sphere has negative Fintucher-Stern invariant, then what is the value of Rs of minus y? So is it always infinite or not? So this might be helpful to answer the question if which is stronger or not. And the second question is a bit classical, but I like this question. So, and moreover, for this work is also motivated by this question. So, yes, is there a cipher fiber sphere bounding a rational ball but D is zero? So this is the last question. And thank you.